Now let's talk about regenerating. We've cleaned the surface. You know, we're using a mechanical, non-abrasive cleaning method. And then what is your, you know, what does the literature say, or what does your research say we should do in terms of we should do, and maybe what we shouldn't do in terms of regeneration, and what's the capacity for regeneration?
Yeah. Yeah, I would say that there are very limited studies. I think, you know, I can only think of a handful of studies that have kind of started to approach that question. And the problem that we've had in the peri-implant literature is that the question you asked before, like how should we clean the implant surface, that hadn't been asked before. So people were thinking really, okay, let's say we clean it with whatever, which most commonly was titanium curettes, and then move on to try 2 different things to regenerate it. Let's see what happens. But the problem is that if you damage the implant surface with these titanium curettes, which for the first time we showed in our clinical trial that's getting published right now, that actually will lead to inability of the site to regenerate, then it's hard to compare the grafts. So I would say out of the very few studies that are available answering that question, where the implant surface still hasn't been destroyed by decontamination methods, we know for one that we cannot use a fastly resorbable biomaterial by itself. So there is a great study by the Stavropoulos team in Sweden where they compared autogenous bone with I think a xenograft, and they found that there was kind of a paradox that autogenous bone alone doesn't perform that well in the context of peri-implantitis. Likely doesn't perform, you know, in terms of that long-term stability. At the same time, our experience has been, and a lot of studies show, that you cannot have a simply osteoconductive graft. Okay. Because if you think about these defects, they're crater-like defects, right? We have kind of a circumference around the implant surface, and the bony walls where the blood supply comes from, they're so far away from the implant that the regenerative potential is really, really compromised. So we have shown, at least on the translational level, that we got to have something better than osteoconduction. So the couple of avenues that we can go at here would be either an osteoinductive graft, so a great quality DFDBA would be one option. Another option would be an osteostimulative graft, so a calcium phosphosilicate graft like the Nova bone morsels we're using in our study would be a combination. And what we're exploring now is the possibility of using either one of those types of grafts or even an osteoconductive graft, but improve its bone building potential by the addition of either growth factors or inductive factors. And examples are the combination of a graft with MD-gain. There's a study from Bern that has tried that with great results in ligature-induced peri-implantitis. Combination of, let's say, FDBA, you know, a graft that's osteoconductive but robust, with PRF, for instance. Or like we do in our study, we're using a combination of the morsels at 70%, and then we're doing 30% autogenous bone, you know, locally scraped it with a microscraper, just to get that osteogenic, osteoinductive potential of the autogenous bone to hype up our osteostimulative graft. But really, the reason why we're doing that is that we've published studies showing that because the surface is not as biocompatible anymore, we need that inductive capacity or that osteostimulating capacity, which means we got to bring more cells early on towards the surface. Because it's a competition, right, between bacteria, soft tissue, and bone cells onto the implant, onto populating the implant surface. And we really want to up the potential of the bone cells to do that first. And if we do that early on, then we can have successful and long-term stable regeneration.